Hello, everyone. Good to be here today, talking about the progress of my PhD from what was I thinking to why am I doing this. Thank you for the intro. And let me start with the next slide. The project is about AI integrated solution for decarbonizing AEC. Pretty big, but with a focus on facade system, so we can discuss about it, what exactly is doing behind it. So this project has two sides: academic side, which I have Professor Haeusler and Professor Sisi Zlatanova as my supervisors, and the industry side, which comes from WT Partnership, which the project is actually funded by them. And I have Jan Badok as the industry supervisor, and that's me in the middle, having some fun, if you believe it. Okay, why do we actually have this focus on facade systems? Pretty easy, because facade systems are kind of the carbon nexus of a building. So if we can actually control what comes in, what goes out within the design process, we can make a huge impact on decarbonizing a building. So keeping in mind that there are variations of different designs, and that makes the process really complicated. So I'm going to put us on dark mode for a bit, and then I will bring you back to the light. So for any decision we want to make, through the process of designing a facade system, we actually have this different driving and responsive parameters when we want to make that decision. For instance, if I want to have a low carbon alternative for my design, how much does it cost if I want to have it? So that's come up with the big question, which is related to making informed decision when we deal with this with the workflow of designing something as a facade system. So making informed decision is not that easy, and you can imagine there are different parameters, different factors that we need to consider, so that it makes it really complicated when it comes to asking an architect, okay, if my design is going to be an alternative, a low carbon alternative, or can I change it to something else? Because the system is itself is really complex, and that actually makes it harder. So considering all of those aspects, if we get into four of them: regulations, cost, material, and replacement interval, which comes from the life cycle of an element of a facade system, we want to, build up a question upon it, getting into a solution, getting into light. So the big question for this research would be, what are the key interactions between those elements that I just discussed, and how we can consider them towards informed decision making in the focus of what we are doing. It because decarbonizing AEC is really huge, but we can't control everything inside the facade system. So finding those interactions requires something, and I want you to think about it in a way that there is an AI that understands geometry. And with that in mind, when it comes to making an informed decision regarding any facade system, like spider cable here with these glazings, all of those factors is behind the AI, and you as an architect or user behind the tool trying to make an interconnection with that system that understands all of those complexity behind it, and it understands like how much cost does it take if you want to change one specific cable here to something that actually has less embodied carbon. So it's not a chatbot, it's a system that thinks, and it is connected to different databases, all related to one of those four components that we discussed. So if we accept the whole workflow we want to use to make an informed decision, reduce the carbon when we want to select a specific material or change our design, this is going to be a simple case for having the workflow. So there are three main components, and each of them is connected to one specific objective. The first component is related to having an AI that understands geometry, as I discussed. And you can imagine with all those fragmented data and different platforms and tools that companies work with, that's a big issue because we definitely need to have a CAD agnostic scenario, which I will be discuss in a moment. And then at the middle, we're going to have the AI tool, which has its own architecture, and we're going to discuss about it. And the last part, which makes the loop coming back between user and AI as two intelligent entity, if we call it, to make the decision. So considering those three main elements, there are four stages of developing such a workflow. The first stage would be translating 3D geometry of a facade system into a graph, and there are some reasons behind it. And the main idea of that is making the 3D geometry in a format that AI understands it. And the two main components in the middle are related to intelligent system, which I discussed. We're going to have an agentic AI system thinking that is connected to the cost, regulations, and building codes, life cycle of any components of the system that we're working on, and also the material, which comes with the carbon and other stuff related to it. The second stage of second component is going to be the reasoning that comes out of the AI, which is inside those agents. Once a 3D geometry goes in the AI readable format, they started to discuss with each other and give the user feedback so you can make the decision. So enough with the diagrams. Let's talk it. What actually are we talking about? So you can imagine this facade systems contains timber frames, metal flashing, and with all those perforations and everything. And the graph at the right side includes all the geometry data inside every single node. Each node represents a specific element of our facade, and the connections between them are based on the adjacency at the moment, but there are some rules behind it. So if you click on every node of this graph, you can see different data pops up, which is connected to that selected element as well. Now, I want you to think about how many different data we can actually extract from different resources and put it on the graph. And this graph is an actual copy of the beam model that we have, because it contains the geometry attributes and it contains all the other attributes that we wanted. So it's like having a graph to be able to read data and write data back to a system. And now you can think about, if I have the geometry data inside this, I can deserialize it in any software or tools that we are working with. And consider the whole workflow as an add-on, as a top-on, like on Revit or on Rhino. Right now, it's working with Rhino, and you can imagine that we can use this workflow on every single tool that we have, or with different approaches. Right now, it's related to facade system and decarbonizing it, but we can think about how else this translation of 3D geometry into something that is AI readable can be useful. So we have gone through this, and at the level of developing the alpha version of this tool, it works like this. The user is behind Rhino. They use our codes and workflow. It pops up in a web-based application, so you can share with anyone. And it understands the 3D geometry into graph that you can see. That's actually the main brain behind it. And you can add, remove components, or think about it that way, that if you select a component and you ask this system thinking, hey, what are my other options related to metal flashing that I selected, but based on the material database that you have, then they start discussing about it and give you some feedback. If you change this to X material, it's going to save that amount of carbon, but you need to be conservative about the cost. So these are the dialogues that we assume is going to happen working with this tool. So to wrap it up, you can imagine that every facade system that's we can translate the 3D geometry into a graph, which is representative of that facade system. And on the right, we have the AI tool that has this ability to discuss between agents from 4 different parameters and give us some feedbacks. And yeah, I'm finished with the presentation, and thank you for having me.
Hey,
Doesn't work.
no, but I can speak quite loud. Trained it. Any questions, please? That finger should work now. Yeah. Haeusler.
Thank you. Great presentation. Thanks for that. So, if I understand correctly, you're considering carbon and cost as parameters. What about other aspects of a facade, such as acoustics, thermal performance?
Yeah, we actually got 4 different parameters to check out the trade-offs: cost, time, building codes, and life cycle. But with other parameters, that actually getting really complicated, and it's out of the scope of this work right now. So the research is about finding these 4 parameters, really, condense, and developing the workflow. Any other factors that is accessible, we can add later on. So it's just open, but for now, it's just those 4 parameters.
Thank you. And also, it's just looking at a single facade material. It's not looking at a composite system of a whole facade system. Yeah.
I assume that we can end up this project with just glazing facade systems, because that's the other issue. We have so many systems out there. We should be selective. But yeah, that's the only thing that I have in my mind at the moment.
Thanks.
Thanks for that. I wonder, could you talk a bit more about how the graph representation of the facade system actually works? Because I was trying to think through, is it essentially a substitution system, or can you make topological modification to the graph? So if I've got a panel, changing it to be made of bread would be much better from a carbon perspective, but from a performance perspective, it's not going to work necessarily. Or can I say, this panel is this high, but if I made it higher, it eliminates other pieces. So
you're talking about the performance that each component can actually get into the process of designing a facade system.
Yeah, and can the AI system remove components or add extras in if necessary?
I believe the configuration ability is the next step of what I'm doing right now. But think of it that way, that okay, if the graph contains all of those geometry data, but by that I mean not just having a mesh that translates the geometry into a data, but having, for example, the rules behind the system, like where are the perforations, where are the bendings, all of this stuff. So imagine we have a graph neural network that understands all of those logics, which are not that many, specifically when we limit the project into glazing system, for example. And later on, somebody can actually work on that idea as another PhD. That, all right, if this graph is quite capable of showing different configurations, or having the performance inside the process of it's like getting insights, that could be useful.
Thank you. Other questions? Yes.
Hey, really enjoyed that. It was a very well put together presentation. Going back to the title of it, AI integrated solutions for decarbonising AEC.
Yeah.
Now, I think the approach that you've taken and the work that you've done around mapping a facade system to a graph makes a lot of sense. Could you describe a little bit how you feel the next steps are to achieving that second highlighted thing around decarbonising? How is it going to help with decarbonising?
At the moment, it's about making informed decision is the big issue behind any step I wanted to go for decarbonizing. And we had no such tool. We just measure carbon. And I was thinking about, okay, what if we can have a system that is intelligent enough to give us some insights for making decisions, regardless of if it's related to decarbonizing it or not. And by selecting different material, when it comes to using different databases that are connected behind this, we can say that, all right, these decisions are connected to decarbonizing, but I'm not claiming about it as a big issue behind this project. It's just one piece out of 100 pieces that we need for decarbonizing.
But I think you've made a bold statement
that
it's going to help with decarbonising the AEC. So yes, it can be one of many, but I think I would expect you to focus actually on what is the yeah, I think you need to focus on actually that particular scenario and run it through from end to end. You've now set up the network, you've kind of looked at how you can collate the data into such a way that is useful and readable and people can actually make informed decisions. Now, how do you run that through? Rather than just saying it can be used for decarbonisation, what is the scenario? And how can it be intelligently used for that purpose?
Okay, let me think about it.
Yeah.
Yeah, at the
It doesn't
moment,
need to be an answer now.
yeah, I know. I'm thinking about, not for getting an answer, to capture what you're actually saying. That would be really good when it comes to how we define the graph, I think. And different people from different profession at our industry can think about it, what workflow we develop to make informed decision. And they, once they understand that, okay, this workflow gives us the opportunity, they can give us some feedback. Maybe I can, use interviews or something to get more of those pieces that I mentioned. That's something that came to my mind right now.
Yeah, I think that's right. I mean, it relates to the previous comment about, if you were to adjust one thing, what would be the ramifications of that? Because fundamentally, your approach in terms of defining the graph is you're exposing the ingredients in the recipe of the building.
Yeah.
So now how do you play with that recipe? Because fundamentally, that's what decarbonisation decision making within industry is. It's how can I tweak this and see what the ramifications are, and does that have a net impact on the carbon intensity of that building?
Yeah.
So I think you need to think about actually how you can make those changes and what happens.
Definitely. Thanks.
You just said
Yeah, thank you. That was great. That's bang on for where I think we are going in terms of agents and AI augmenting human performance and thinking about those agents as a team. You've got the cost team, the materials team, and so forth. Have you thought about how to layer memory over the top of that team? Because I think as a project progresses through its life cycle, early on, you want that team to be a little bit more exploratory. Like, yep, try this, try that, try something else. As you get later in the progress of the project, that memory will inform previous decisions that were, turned down, and might, eliminate them from what it does propose.
Okay, yeah, thank you. That's an interesting question and is part of the process. You see these two main components for the intelligent system. We're thinking of having a land graph on top of different nodes that we have for making those decisions. Those nodes are the agents for us. Not all of them are AI agents. Not necessarily we need that, but for cost, for instance, and building codes, we're going to have AI agents to go through the process. And every decision making coming through the loop between the machine and human is going to be saved inside the memory behind the land graph. And we're going to actually we're thinking about it, refining the system via those memory that we actually captured, and that's a part of the process.
Hi. Yeah.
Hello.
I was just wanting to know a bit more about how you've gone about your carbon calculations and where you've gotten the data from, whether it's volumetric or whatever else, environmental product declarations, those sorts of things, because I know there's a bit of disparity in what is declared from manufacturers and what materials that they actually have been using throughout that process. Yeah, I'm just wanting to know a bit about where that's all come from.
Yeah. We have 3 databases, EC3 neighbors and Green Building Council of Australia also has a specific database for different materials, and we're going to use them during the process of selecting a specific one. And we also have, since this is facade system, we're talking about different products like aluminum products, profiles, or these kind of stuff, specifically when it comes to glazing facade systems. We also have the catalogs of the manufacturers that has their product tested, and they need to provide carbon measurements as well. So it's just like a simple function getting into the database, getting the info and put it on the 3D model. That's it.
So, hello, Mahdi. Excellent presentation. And I'll build on the question that you got from the audience and more on the system side. So if you scale up this workflow to multi-agents or include memory on it, I would have liked to see how you are, and I'm assuming your databases are online databases. So I would be more interested in how you are doing the hardware tool chain to run all this.
Yeah.
And would be interested in sharing my notes as well in the evening if you want, if you have time.
Yeah, of course, I'm happy. And you know that part of this project is highly related to yours. That's the reason. And for the databases, I was thinking about having them connected to a system online. But that brilliant woman behind you, which is my supervisor, Sisi, told me that, hey, you need to think about having your own database, at least for running the workflow. Yeah, exactly.
Prototypes of on-premise, we can share them.
Definitely. Thanks.
Yes, ma'am. Thank you so much. It was really interesting to see the evolution of your work on the subject. And now the way I see it is more of architect interaction with the graph. You know, that's really your main thing that you are bringing at the end. And when I look at it in terms of the subject matter that you're dealing with, which is the facade, so architect interaction with the graph with the aim of decarbonization or reduce, the carbonization. But the facade traditionally being designed with 2 aims, which is first is the performance aim, which is in terms of thermal performance, sound performance, whatever, and the second one is the aesthetic, the style of the architect that wanted the facade to be this way. So if the tool try not only looking at decarbonization in terms of material usage and color and the specification, the regulation, but with the aim of reducing or enhancing the performance, a particular performance, because it's a really more of a multi-objective process or optimization here. What the tool try to do, you cannot decarbonize the material if that's going to worsen the thermal performance of that facade, internally, because your net carbon is not only the material itself, but it's actually the energy consumption that is happening because of this facade treatment inside. So that kind of net carbon is what the tool I think needs to look at. And when AI intelligence comes in, says, well, I can't change that topology or composition this way, but then the net performance inside, that's the negative or reverse impact on it. So I think it needs kind of to look at both in terms of topology, geometry, as well as the net performance.
Thanks. That's a good point. And last time that you actually brought that idea up in my head, I was thinking about the embodied carbon and operational carbon in a 2 level that we can see this project from. And we can think about it, when it comes to having all of those attributes regarding aesthetic, performance, these stuff. And if we have this system, we also can connect it to the whole building performance in the next stages.
Thank you. Are there any other questions? Yep.
Great presentation. I just want to know a little bit more about how you possibly go with translating the facade into the graph. Like how you're thinking of tackling that problem, and what is the connection between the nodes? Like, are you thinking non-manifold geometries like based on the adjacency, or like what's your?
It's based on adjacency at the moment, but it's not just if this object is connected to this one, there's going to be an edge connecting them together at two nodes. It's more than that. It understands the semantic connections between them. Like if there is a perforation in this element and there is just another like connecting element on this, it understands them and put it together with an edge. Right now it's an adjacency, but I'm thinking about having more attributes to the edges. And the process is having a mesh version of the elements, because that's to the objects we're talking about. But that mesh includes all of these, like connections between the elements as well inside it, like the logic behind the facade system that is included in that specific one we're talking about. So imagine all of these information has been sorted in a JSON file, categorize them based on a schema that is our system and our AI can understand them. And this is the way we manage it through the process of translating 2D geometry into something that AI understands. There's a missing part here. And that missing part is having the insights in natural language for every element that we have, or for the whole facade system that we're talking about. Those insights are from the engineer, from architects, whoever is behind the system, and are collected, for example, at the end of that JSON file related to every element that we have. For example, we have this cable structure here with this spider system checking, or better say, holding the glazings. And there are some specific logics behind the design of this system, like constraints, limits, structural, structural behavior that we need to consider. These are in natural language inside that JSON. So AI can understand this information, and also it has the geometry data as well. So this is the whole JSON that is a translated version of the 3D geometry. It's not just about the meshing vertices and edges.
I think we've got time for one more question.
Can you give us an example of the output? What could we expect as a feedback?
Yeah, sure. So imagine this intelligent system is at the back end of Rhino. You're working on inside Rhino, and you want to check your design if there is an alternative for this glazing, for example, that is that comes with a low carbon. So you ask it in natural language, like a chatbot at that point, which is the endpoint, and it's go through the process, analyze your request, and give you some feedback from the database that, hey, there is, for example, more low carbon like alternative you can use for your glazing with the same performance, with the same like limits and constraints that your system has, and you can use it, but it comes with this top-up cost. Do you want to exchange it or not? So I'm thinking about that is why we included geometry like data inside the graph. And in that case, you can actually select that low carbon alternative, provide that component inside your 2D model. This is the process that we're imagining right now.
Good. There are many other tricks underneath the hood as well that I'm happy to discuss later. That's outside the PhD kind of topic, but are very, very interesting as subsequences of the tools that have so far been developed. Thank you very much for your presentation, Mahdi.